Jai Hind students. Similarly, in the first two units, again in unit 3rd, I am going to cover the most important topic of this unit, and that is QAM. Before going towards QAM, I want to give you some brief discussion about this unit 3rd. That in telemetry systems, actually we are working on the complete telemetry system, that what are the main component of a telemetry system, how you are going to design a telemetry system to send a specific sensor information to the remote location. For all these purposes, first of all, you have to identify that what are the basic building blocks of a telemetry system. As I told you in first unit, the main part of a telemetry systems are transmitter, then channel, and then receiver. Basically, transmitter is generating the information coming from the sensor and getting that info in the form of the EM waves or through the wired channel. So, to transfer that data from transmitter to this channel, we required some specific kind of instrument, and that is called modem. Actually, third unit is about the modem, and that modem stand for modulation demodulation, means a equipment which is performing both modulation and demodulation at the same time as per the requirement of the system. So, in this diagram you can easily understand that there is a computer or another users, they are creating some data. That data is going towards modem through the routers, and then that modem is sending that data either from wireless or wired. For wire you are using the DSL, ADSL optical links, or for the wireless you are using the RF systems. So, this is the antenna that is used for the wireless medium, and similarly at the receiver side you are getting the data. So, this is the main thing about that modem. That modem is a basic device which is going to be used for the modulation as well as demodulation process. Means simultaneously on the modem, on the same time, modulation is also going on and demodulation is also going on as per the system. So, here you can see the internal building block of a modem. In modem, there are two parts, that are transmitter and receiver. Transmitter is basically performing the modulation, and receiver is performing the demodulation. Other than that, there is a digital interface that is basically connecting the distance terminal equipment DTE to the modem, and another point is line interface, which is actually connecting the various telephone instrument or transmission medium through the modem. So, this is about the complete structure of a modem. And if we talk about that modulation technique or demodulation technique, we have to consider the modulation techniques used by the modem. So, in modem there are many techniques, and the most frequently used modulation technique of modem are FM, AM and phase modulation. But now you can easily understand one point, that if we are talking about the noise immunity, the amplitude modulation have the minimum noise immunity, whether phase modulation is the best as far as we are considering the various characteristics of the modulation technique. So, you can see that some points are very good in amplitude modulation, whether some points are very good in the phase modulation or frequency modulation. So, in basic modems, they are basically using a combinational modulation, or we can say that hybrid modulation, which stand by QAM. Actually, here Q stand for the quadrature, A stand for the amplitude and M for modulation. In this modulation, we are actually using two modulation, which one? Phase modulation and also amplitude modulation. Means we are using a combination of amplitude change and the phase change. So, how it is going to start? So, first of all, the modulation technique. So, in the terms of the description, you can see that the information such as sound, audio, images and digital data can be transmitted from one point to another using the radio waves, and that is done by the modulating an RF signal and a carrier with the information to be transmitted. So in the modulation, what we are actually going to do, in the modulation, we are taking a carrier signal which is having a high frequency, and that high frequency carrier signal is going to be modulated as per the instantaneous value of the message signal or the information signal. After that, we are getting a modulated signal, and that modulated signal is going to transfer from wireless or wired medium. So starting from this modulation techniques, actually we have two types of modulation techniques: analog modulation and digital modulation. Means when we are talking about analog modulation, means we are using a analog signal for the modulation, or in the case of digital modulation, we are actually applying a digital signal on a carrier and we are performing the modulation. So when we are talking about the analog modulation, you can see here there are three types of modulation: amplitude, phase and frequency. Any signal having basically three parameters, that are amplitude, phase and frequency. And in the analog modulation technique, when we are changing the carrier amplitude as per the instantaneous value of the message signal, then it will become the amplitude modulation. Similarly, when frequency of the carrier is going to be modulated, then that is a frequency, and in the case of phase variation, that is called phase modulation. These waves are actually representing the all three modulation technique, and here you can consider this is a analog modulation technique. But when we are talking about the modem part, we are actually going towards the digital modulation technique. In digital modulation technique, actually we have a amplitude shift keying, phase shift keying and frequency shift keying. Three techniques are there. These techniques are same as AM, FM, PM. But what is the main change? In AM, FM, PM, our input signal is a analog signal, and the carrier signal is also a high frequency sinusoidal. But when we are talking about the digital modulation technique, in this technique our input signal is in the form of 1010110 in this kind of digital signal, which is going to be represented by a specific line code such as unipolar, RZ, unipolar, NRZ, polar RZ, polar NRZ, as per the modulation technique. And then that input digital signal going to modulate this sinusoidal carrier, and we are getting this type of modulation. So in basically when we are talking about this QAM technique, actually we are taking the main characteristics of ASK, means amplitude shift keying, and the phase shift keying, and by combining both of them we are getting a quadrature amplitude modulation. So before going towards that quadrature amplitude modulation, you have to understand what is ASK and what is PSK. So here you can see that this first one is this second one, this is ASK. Here you can see that this is the modulating signal, means that is the message signal. In message signal we are getting a 0 followed by a 1. Then if we going to use this message signal to modulate this sinusoidal carrier, then what will happen? That sinusoidal carrier is modulated as per this incoming 0 or incoming 1. So as per the logic set by the system, the part of the amplitude of this carrier will going to change. You can here see that for the 0 the amplitude is same, but for the 1 that amplitude is going decreasing. Means whether sometimes that case is also coming when if you are 0 and 1 you are modulating this signal, you will get this kind of signal. Means when 0 is going to transmit, there is no signal. When 1 is going to transmit, a original carrier is going to be transmitted. So you can see here that at the 0 point there is a off, at 1 there is a on. Means this is also called on-off keying technique. These digital modulation technique are known as shift keying techniques, because these bits are actually providing the key to the system so that the phase, amplitude or frequency of the carrier is going to change or vary as per the bit. So here in ASK they are directly doing this on off, that's why it is also called as on off keying. The most easy example, the advantage of this ASK is that ASK circuit is quite simple to construct. That's why we are using this as ASK characteristics for the hybrid modulation. When we are talking about the FSK, in FSK we have to change the frequency, and shifting of the frequency is not a very easy task. Similarly, in PSK we are varying the phase of the carrier as per the instantaneous value of the digital bits. So in the PSK, the most the best thing about this PSK is about its noise immunity. Basically, PSK signals are very immune to the noise. That's why when we are talking about the noise immunity part, PSK is the best suitable. Then the noise immunity, then the PSK is the best suitable, FSK is the second one, and ASK is the least one. So by combining these two parameters, in ASK it is quite simple, and PSK have its noise immunity. We are going to create a new hybrid modulation technique, and that is called QAM. So how we are going to perform this QAM? Actually, in QAM, when we are talking about QAM, that Q stand for the phase change, and that stand for quadrature. So when we are talking about quadrature, that what is quadrature? In quadrature, actually you are taking a phase shift of 90 degree. Here you can see that there are various waveforms draw here, and each waveform have a individual carrier phase. Means you can see that this wave has a 0 degree phase, this has a 45 degree, this has a 90 degree, similarly so on. So these graphs represent actually RF carrier in time domain with different phase relative to one another, and they all have the same frequency and the same amplitude. So assume that here the top carrier is assigned a arbitrary phase value of the 0, then the second carrier phase is relative to the first one is delayed by the 45 degree. Similarly, third one is delayed by 90 degree in respect to this. Fourth one is 135 degree in respect to this. So this is about the carrier phase. So what we are going to do here? We are using this in phase quadrature modulation technique. I stand for the in phase and Q stand for the quadrature. When we are talking about the quadrature and in phase, you can here see that we have a number of sequence, means we have a bit sequence of 1 0 1 1 0 1 0 1. Here you can see that these are the bit number 1 2 3 4 5 6 7 8. So what we are going to do in this in phase and quadrature amplitude quadrature modulation, you can here see that we are using two carriers. One carrier is in phase, means the phase shift, the phase is delayed by 0 degree in the in phase carrier. But when we are quadrature, that is delayed by 90 degree, as I show in this previous one. Means one in phase is this and quadrature is this. Between them there is a 90 degree phase shift. So here you can see that there is a local oscillator to generate the carrier frequency, and that local oscillator is providing that carrier frequency to this lower part in phase, whether in the other one multiplier, that is the carrier is 90 degree phase shifted. So what is the next signal? This Q and I signal are coming from this bit sequence. So how it is created by I and Q? Actually this I and Q are going to design by dividing this bit sequence into two parts. First one is odd sequence and second one is even sequence. So what we are doing, in odd sequence we will take only first, third, fifth, seventh, ninth and so on bits. In even sequence we are taking 2, 4, 6, 8. So in phase we are actually taking the even sequence, and in the odd sequence we are using this 90 degree phase shifted quadrature carrier. So this even and odd sequence are modulated by two different carriers, and at the summer point these both in phase and quadrature modulated signals are going to be combined and we will get a in phase quadrature modulated waveform. So in this technique actually we are using two different carriers. So what is the main help of this? That one path is delayed by the amount of time equal to the 1/4 of the carrier cycle time, and that is 90 degree. So the two carriers are amplitude modulated one by I and other by the Q, and the two modulated carriers are added together in a summing circuit. So the output is digitally modulated signal whose amplitude and phase are determined by the amplitude of the two modulating signal. So you can here see that in basic terms that point is going to be covered by the QPSK. So what is this QPSK? Basically QPSK is about the quadrature phase shift keying. This is a type of hybrid modulation also, but in this we are only taking the phase shifting part. So the limitation of this QPSK is that we are only transmitting 2 bits simultaneously, one per channel. Means if we have a signal 0 1 1 1 1 0 0 1, means we are going to make these 2 bits simultaneously one per channel. So what we are going to do here, you can see that these are 1 2 3 4 5 6 7 8 bits. Again doing the same practice as shown here, we are actually changing the phase, one for quadrature and one for in phase, and using the same odd sequence and even sequence to modulate the system. So here you can understand that QPSK, what are going to happen when we are talking about the Euclidean space Euclidean coordinate system to represent this digitally modulated signal. We have a in phase carrier axis, quadrature carrier axis, and the 4 quadrant are representing the all 4 possible bit sequence of 2, because when we are taking 2 bits there are only 4 combination 0 0 1 0 1 1 1. So you can see that 0 0 is lying here, 0 1 here, 1 0 here, and 1 1 this. So what is the combination? Here you can understand that quadrature phase shift keying means shift among the phase state by 90 degree, and the signal shift in increment of 90 degree from 45 degree to 135, and data into the modulator is separated into 2 channels I and Q. 2 bits are transmitted simultaneously, and each channel modulate a carrier. The 2 carrier frequencies are the same, but their phase is offset by 90 degree. So the total possible states in this QPSK modulation are 4. That is because of 2 the power 2 is equal to 4. Then this is the QPSK modulation mapping, symbol mapping. So as per this symbol mapping and as per the carrier phase delay, you can easily see here the system symbol transmitted. So when we are transmitting the symbol 0 0, the carrier phase is 225 degree. When 0 1 135, 10 315, and 11 45 degree. And for all them carrier is basically 1 only. So you can say that that amplitude is defined by this Euclidean distance. This is the Euclidean distance. So you can here see that in the next diagram also. This one is the fun. If you are going to transfer the 0 0, means the phase shift value is 225 degree, and the Euclidean space is this one is considered. Similarly for the next one 0 1, this one, then 1 0, this one, and for the 1 1. So you can easily understand these points, that how your signal is going to be transmitted. So now about the QAM modulation. Actually in QPSK you are taking 2 bits at a time, but in QAM actually there is no constant about this bits. We are taking number of bits, means we can use 2 bits, 4 bits, 3 bits, 5 bits, 6 bits, and as per these bits we are going to create QAM system. Means if you are using 2 bits, means to the power 2, 4 means 4 QAM. Similarly, when we are talking about 2 to the power 3, that is 8, means 8 QAM. And the most common and famous is 2 to the power 4, that is 16 QAM. So basic modulation technique for this QAM technique is same as for the QPSK, means you are going to use a quadrature signal and another one is a in phase carrier. So you can here see that the quadrature amplitude modulation is a form of modulation that is widely used for modulation data signal into a carrier used for radio communication. And in this quadrature amplitude modulation, a signal in which 2 carriers shifted in phase by 90 degree are modulated, and the resultant output consists of both amplitude and phase variation. In view of the fact that the both amplitude and phase variation are present, it may also be considered as a mixture of amplitude and phase modulation. So this is the diagram. Here you can see that it is as equivalent to QPSK, means to the power 2 4 states of operation of QAM. This is the bit sequence 00, 10, 01, 11. You are here taking the odd bits. These are the odd bit sequence only. See 00, 1, 0, 1, and that odd bit sequence is going to be modulated by sine wave, and you are getting this odd bit sequence modulated signal. Similarly, for the even bit sequence, you are taking the 0, 0, 1, 1. This is the example. For this odd bit sequence, you are taking the cos, then again getting the odd bit odd modulated signals, and by combining these both two, you will get this. Means here there is a 2:1 converter, means providing even and odd. Then even is applied to this multiplier, from where 0 degree phase shift carrier is coming. After modulation, getting the even modulated bit sequence. Here we are getting the odd modulated bit sequence with a 90 degree phase shift carrier, means quadrature carrier, here in phase carrier. By combining both of this, you are getting this. So if you are talking about the specification, you can see here quadrature amplitude modulation is used for digital transmission for radio communication application, and it is able to carry higher data rate than the ordinary amplitude modulated scheme and phase modulated scheme. So the number of points at which the signal can rest, the number of points on the constellation is indicated in the modulating format, means 16 QAM uses 16 point constellation. Similarly, there are various other constellation are also possible, such as 4, 2, 4, 8, 16. And if you can see that for 2 bits are 1, for 4, 2, for 8, 3, 4, similarly so on. So by using this QAM constellation diagram, you can understand that by using higher order modulation format, more point on the constellation, it is possible to transmit more bits per symbol. However, the points are closer together, and they are therefore more susceptible to noise and data errors. So to provide an example of how QAM operates, the table below the this table, you can see here, this is the table. That table is showing you the basic constellation, means this is a part for the 16 QAM. Here you can understand that 16 QAM means you are going to use 4 bits. For 4 bits, the total combination is possible 16, and then 16 combination are 00, 00 to 11, 11. Now you can see the carrier phase. There are 4 carrier phases are possible: 45 degree, 135 degree, 225 and 315. But for each constellation, this is the constellation diagram: in phase carrier, quadrature carrier. So you can see here in this quadrant, these 4 have the individual Euclidean distance, and that Euclidean distance actually defining the carrier amplitude. So for the 0000, you have a modulated signal with a carrier phase of 225 degree and the carrier amplitude of 0.33. So similarly, you can get all these data as per your system requirement, and you can understand here that for all individual signals, you have a different set of phase and amplitude. So here you can see that when we are talking about the 4, there are, this is constellation diagram of 4 QAM. This is the constellation diagram of 16 QAM. So number of points are increasing as you are increasing the number of bits. And in 4 QAM, you are sending 2 bits per signal. In this, you are sending 4 bits per signal. And similarly, if you are talking about the 8 QAM, then you are sending the 3 bits per signal. So when we are concentrating on 16 QAM, these are some specifications that for 16 QAM, there are 16 states, means 4 in phase values and 4 quadrature values. Then theoretical bandwidth and efficiency is 4 bits per second per hertz, and the data is split into 2 channels I and Q, and as with QPSK, each channel can take 1 2-phase. However, 16 QAM also accommodate 2 intermediate amplitude values, and these values are such as 0.75, 0.33 and 1. So these values are also defining the 16 QAM, and the 2 bits to each channel are added, then applied to the respective channel modulator. So this is about the 16 QAM constellation diagram. Similarly, here you can see that if we are using the gray code symbol mapping for this QAM technique, then this constellation diagram will change, and the individual dot or individual signal is represented by that phase and amplitude combination is coded in the form of gray code. You can also use the differentially coded symbol, and for the differentially coded system, this is the constellation diagram of 16 QAM. So here you can understand one very clear point, that what are the basic application of a QAM. So basically QAM is in many radio communication and data delivery application, and in some specific variants of the QAM that are used more specific application and standard for the specific purpose of radar or something else. So for domestic broadcast application, for example, 64 QAM and 256 QAM are often used in digital cable television and cable modern application. In the United Kingdom, 16 QAM and 64 QAM are currently used for digital terrestrial television using DVB, digital video broadcasting. In the US, they are using 64 QAM and 256 QAM are the mandated modulation scheme for the digital cable as standardized by the SCT in the standard NC SCT 07-2000. So these are the specific application of QAM. They all are using the specific point QAM for the specific operation. And other than that, variant of QAM are also used for many wireless and cellular technology applications. So the main advantages of these QAM are that QAM appear to increase the efficiency of transmission for the video or for the radio, and also communication systems by utilizing both amplitude and phase variation are also a advantage of QAM. But rather than that, there are some disadvantages also, and that disadvantages are that QAM having number of states, and if the states are close together, so they are more susceptible to the noise, because that a lower level of noise is needed to move the signal to a different decision point. And the receiver for use with phase and frequency modulation are both able to use limiting amplifier that are able to remove any amplitude noise and thereby improve the noise reliance. This is not in the case with QAM, means that use of these amplifier are not in the case with the QAM. So this is also a disadvantage. Then the second limitation of the QAM is that also associated with the amplitude component of the signal. When a phase or frequency modulated signal is amplified in a radio transmitter, there is no need to use linear amplifier, where as when using QAM, they contain an amplitude component, a linearity must be maintained. So unfortunately, linear amplifier are less efficient and consume more power, and this makes them less attractive for mobile application. So when you are using this QAM for the mobile application, you have to change this linear amplifier, because of that limitations of less efficiency and more power consumption. So these are the some disadvantages of QAM. So in this third unit, you can easily understand some points that QAM is the main technique which is going to use by modem. Other than that, modem protocol is also another example. Modem protocol that are also a very important topic of this third unit. So you can understand that also, because exam point of view it is also important. So thank you so much. Jai.